All right, everybody. Hello. Welcome to the first video on electrons and light. So we've already done a little bit of discussion on these first two questions, right? Where does light come from and what is light? Today in this video, I want us to focus predominantly on how can we quantify light? All right, so we've already learned a little bit about these equations, but I just want us to get a little bit more familiar with them and so that you can use this video to help you substitute for the homework that you'll be working on later today and through the rest of this week. So we've been working a lot with these equations. So we have C is equal to lambda V. We have E is equal to HV. And now we have this new variation, which is E is equal to N times HC over lambda. Now what I want us to do, although we already did this in class, I want us to review how did we get equation 3 from these first two equations. So let's spend a little bit of time on this. So these first two equations, you're actually not going to be using that often. These first two equations are more of a stepping stone into equation 3 because we already know the relationships between light and frequency and wavelength, right? But now what I want us to do is to actually apply wavelength with energy, right? Because none of these equations here and here, 1 and 2, they don't have any definitive relationship between wavelength and energy. It wasn't until we combined them and reorganized them to get this equation that shows us the relationship between wavelength and energy. So as we discussed, we said that the thing that is similar between equation 1 and 2 is frequency, which is V. So if we set both of these equations, 1 and 2, equal to V, we rearrange them into V is equal to C over lambda and V is equal to E over H. All right, we know that the frequency of both of these equations is the same because, again, we're referring to the same photon. So let's call this packet, it's not a mitochondria, it looks like a mitochondria. This is our photon, poorly drawn one. The frequency is going to be the same for both of these equations because we're referring both of these equations are referring to that same photon. So we set them both equal and we combine them to get V is equal to V, which is equal to C over lambda, which is equal to E over H. All right, now what we can do is multiply H on both sides to get E by itself, which gives us our equation E is equal to HC divided by lambda. But now you may be wondering, well, Mr. B, that's not exactly right. E is equal to HC over lambda is not the same as E is equal to N times HC over lambda. Well, you're absolutely right. That is a very important aspect to understand, right? This HC over lambda is what Einstein called a quanta. Okay, so a quanta is the amount of energy in this photon. So the energy that is possessed in that one photon is referred to as a quanta. So photon is a thing, right? Quanta is the energy of that thing. How much energy does that thing have? And we can represent this with this equation. So let's say, for example, I had 3 of those photons. All right, so let's say I had 3 of these photons, and I wanted to figure out what is the total energy? What is the total energy of all 3 of these photons? All right, let's say each of these photons has a wavelength that is equal to, let's say, 500 nanometers. So how would we figure this out? Well, this is actually going to be a fairly straightforward plug and chug approach. So what we're going to do is we're going to take the 500 nanometers and we're going to plug it in for lambda. And before we plug it into lambda's nanometers, we have to convert it to meters. But let me show you why we have to first. So again, we take ET. We're trying to find the total amount of energy that these 3 photons possess. So we have ET is equal to, well, my N here is going to be 3 because we have 3 photons or 3 quantas of energy. H is 6.626 times 10 to the negative 34, joules per second. I'm so used to moles. Times C, which is the speed of light, 3 times 10 to the 8th meters per second, over our lambda. But look, this unit here of our speed of light is in meters. Also, joules is measured in meters, meters squared. So we have to use meters, right? If we don't use meters, then we're gonna have to convert both of these constants into nanometers, which will make our life a lot more tricky. So we don't wanna do that. So let's first convert our 500 nanometers into meters. So how many meters is in 500 nanometers? So again, as I illustrated in class, it is very important to not try to be fancy here with our moves, okay? We just wanna get the job done and get our answer. So we take these 500 nanometers, and what I'm gonna do, I didn't mean to cross that out. 500 nanometers, I'm gonna cross out the NM, and that crossing out symbolizes that I don't want nanometers, I want meters, but that also is gonna substitute as a multiplication. So times 10 to the negative 9 meters, right? And that should be intuitive. Negative 9 meters, that is 500 nanometers is a very, 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 very small amount on our meter stick, right? On a meter stick, I could go all the way down to 1 millimeter, but a nanometer is far smaller than just a millimeter. So we're going even smaller. So 500 nanometers is barely making a mark on our meter stick. Okay, so I'm going to use this number and plug it in, 500 times 10 to the negative 9 meters. All right. So we get a total amount of energy of 6.626 second e to the negative 34. Multiply that by 3 second e to the 8th, and we get 3 times 1.989 times 10 to the negative 25th joule meters. All right, now, honestly, I've memorized this number more than I've memorized Planck's constant, and that's just because I've done this calculation so many times. So it may be beneficial if you're really struggling to get these problems done in a meaningful amount of time. It may be helpful just to memorize this, because both of these terms, Planck's constant and the speed of light constant, can be multiplied into a new constant, right? There are two constants being multiplied, so it should be the same every time. It will be the same every time. So 1.989 second e to the negative 25th. And we're going to divide that by 500 second e to the negative 9, or times 10 to the negative 9. And we get, sorry, I forgot to write it down, meters. And we get 3 times 3.98 times 10 to the negative 19 meters. Sorry, joules. Right, the meters canceled out. So now we can take our E and multiply that by 3, and we get a total answer of 1.19 times 10 to the negative 18 joules. Now, as I've been mentioning, these numbers are going to be incredibly weird for us to wrap our brain around, right? We're not used to dealing with these really large numbers or really, really small numbers, but all I want you to understand is if it's 10 to the negative something, that usually means it's very small. So when we're dealing with energy, like the energy is equal to 1.18 or 1.19 times 10 to the negative 18 joules, it should be incredibly small. We're talking about 3 photons, right? When you turn on your computer screen or you turn on a flashlight or your phone's flashlight or whatever, you are emitting billions and billions and billions of photons at a time. And if you shine that on your skin, right, nothing really happens. It's not that high of energy. However, if you go to, let's say, a tanning salon, that's UV light that we're talking about, and it's usually moles of photons. So let's use that as our next question here. So UV light, I'll give you a second, is it more energy or less energy than visible light? So I'll give you a second. Right? It's more energy. UV light, right? You can go out in the sun. Again, you can go out in the sun whenever you're walking around or whatever, and usually you're fine. But if you're out in the sun for a long time, like on a beach or what have you, you may be exposed to a lot of UV radiation. And that UV radiation can be bad, right? But we're also exposed to visible light radiation all the time. So that radiation, again, isn't necessarily a bad term, but in our case, UV radiation can be harmful for us specifically over a long period of time. So with that being said, so let's say you go to a tanning salon and they're emitting UV light, which is roughly, let's say, 100 nanometers. Okay, and this 100 nanometers, and let's say that you're in the tanning bed for, let's say, 1 hour. That seems a lot. Let's say 30 minutes. And the tanning bed says that it emits 3 moles of UV light every 5 minutes. All right, I'm making this up. I have no idea. So 3 moles of UV, it's probably even more than that, to be honest. So let's calculate how much energy this is going to be. So we want to know how much energy of light are we going to receive in one session at this tanning salon. So how much energy we receiving I before E except after C. Receiving. Are we receiving at this tanning salon? All right. So 3 moles of UV light every 5 minutes. Now I'm going to erase this just to give myself a little bit more room here. 3 moles of UV every 5 minutes. And we're in the tanning bed for 30 minutes. So let's first just figure out how many moles of light we're working with. So 5 minutes, it's 3 moles. So 10 minutes, it's 6. So 30, that means it's how much? 18, right? So 18 moles of UV light in that 30 minutes. And that's a pretty big number. So how much energy are we receiving at this tanning salon if we're in this tanning salon for 30 minutes? So we already did the 30 minutes, so let's cancel it out so we make our lives a little bit more simplifying. So we have 18 moles, and again, we have UV light at 100 nanometers. So I'm gonna go ahead and convert that 100 nanometers into meters, and look at that, I'm already done. 100 times 10 to the negative 9. So now let's plug it all in. So energy is equal to N times HC divided by lambda, which I'm going to rearrange as 18 times 6.022 times 10 to the 23rd. Now, I want to be very clear here. A lot of students still make this mistake when when we are plugging in moles. Remember, there's a difference between what we just did, meaning we have 3 photons and we calculated the energy of each of those 3 quantas of photons, the energy of each of those photons, versus 18 moles, right? If I said 3 moles, that is a lot more photons of energy, or a lot more quanta of energy. So if we're to say 18, or let's just say 3 moles, well, the calculation would come out the same. If I assumed it was 3 moles, if I said N is equal to 3 moles, then our answer would not be the same. Okay, so we have to plug in 6.022 times 10 to the 23rd in order for us to get the true value of how much energy is there. So 18 times 6.022 times 10 to the 23rd photons times each of those photons' energy, which again, I'm already going to make the summation of 1.989 times 10 to the negative 25th. If you're a little bit confused about how I got that, just review back to a few minutes ago. Meter, divide that by the amount of wavelength, which is again 100 nanometers, but again, we have to do it in meters, so it's 100 times 10 to the negative 9 meters. Again, I'm not going to be fancy. I'm not going to do 1 times 10 to the negative 9th. I'm just going to keep it as is. So let's go ahead and do the quanta part. So E is going to be equal to 1.989 times 10 to the negative 25th. Divide that by 100 to the negative 9. And we get 18 times 6.022 times 10 to the 23rd. Now, this is also another lesson on what my professors used to tell me all the time, actually, is don't be a calculator hero, right? So what I mean by that is don't plug all these numbers into your calculator at once because you're bound to make a mistake. Human error is inevitable with these types of problems, especially with all these times 10 to the negative whatever. So it takes a lot of parentheses and, entering it into the calculator correctly. So I'm just going to do it piece by piece to mitigate any error that could have been caused by me. So I kept the 18 times 6.022 times 10 to the 23rd off to the side for now. I did the one calculation. I got 1.989 times 10 to the negative 18. Again, the meters canceled out, so I'm at joules here. And notice how there's no units here for 18 times 6.022 times 10 to the 23rd, right? It's just a number of things, right? We had that many photons. So E is equal to, now let's multiply the number we just got by 6.022 times 10 to the 23rd. And then let's multiply it again by 18. And we get a very large number. I'm going to put it in scientific notation. 2.16 times 10 to the 7th joules of energy. Now that is real energy. Okay, this could actually do something. All right. Now, it may be advantageous for you to play around a little bit with the different wavelengths and see how it changes the amount of energy. Okay. So as we know, the shorter the wavelength, the less we're dividing this number by, meaning the more joules we'll be having, okay, or the more energy. So energy and wavelength are inversely proportional. All right, I hope this video helped you a little bit, at least organizing some of your thoughts here, and hopefully it'll help you for the homework. Again, these other two questions, where does light come from and what is light, we'll be answering those questions in the coming few lectures. And I think that's really what's going to bring these two sections together. These two things that we've barely been talking about together perfectly, which is electrons and light. All right. Have a great rest of your day, everybody. I hope this helped. I'll see you all tomorrow. Bye-bye.